Welcome back. This is an Aleks training video on calculating the wavelength of a line in the spectrum of hydrogen. Every element is going to give a specific fingerprint of bright lines or dark lines that are going to be emitted at certain frequencies. And the certain frequencies have to do with the electrons that are surrounding that nucleus are going to be energized. If you were to say shine light on an element or heat an element or do anything that's going to give it energy, then the energy is going to be absorbed by that electron, whatever the electrons are in that atom, and they're going to be excited to a state farther away from the nucleus than they normally live. So they're hyper and they're going further away, and then when they drop back to their normal state, they emit a photon of light equal to the energy that they absorbed. So if they absorb 25 cents worth of energy, they go up to an excited state, and then when they drop back to their normal state, they emit a photon. So every single element is going to have a specific set of energies that they're going to emit as the electrons are absorbing energy and then dropping them back and emitting energy. So if I have, we're going to use the Bohr model. This is the Bohr equation right here. So the energy is equal, the energy that is absorbed or the energy that's released as it shines out a light is going to be equal to, and then this is R sub y, which is the Rydberg energy constant. You can find this on the data table in the Aleks. I've given it to you here, 2.17987 times 10 to the negative 18 joules. And then this is going to be over whatever energy state that it's in. So the ground state would just be n equals 1. If it goes up to an excited state of 2 or 3 or whatever, this problem is saying that you're going up from a state of normal 1 up to an excited state 11. All right, so the energy is going to be the total energy, or the change in energy, is simply going to be the energy of this excited state, 11, minus whatever the original energy was. Okay, so whatever the energy it was at normal, subtracted, that's the energy that's going to be emitted as a photon. And then you can use that energy to find out what the wavelength of that photon will be, what the color would actually be. All right? Okay, so if I have, again, delta E equals energy at 11 minus energy at 1, I'm just going to substitute the Bohr model for each of these energies. I'll say that the change in energy is going to be equal to negative Rydberg over 11 squared minus, and then this is minus again, the Bohr model at 1. 1 squared. Okay, so when I substitute this, it's going to be negative 2.17987 times 10 to the negative 18 joules over 11 squared minus 2.17987 times 10 to the minus 18 joules over 1 squared, which is 1. Okay, when you do the arithmetic, you're going to get the change of energy equals 2.1619 times 10 to the minus 18 joules. Okay, so now, since I know the energy of the photon, I can use the relationship between the photon energy and the wavelength to calculate the wavelength. So this is Planck's rule. The energy is equal to Planck's constant times the speed of light over the wavelength of the energy. And I'm going to solve for wavelength. So I'm going to have lambda's wavelength equals Planck's constant times speed of light over its energy. Okay, so that means that lambda is going to be equal, I need Planck's constant, which you can look up in the data, table again. This is Planck's constant here, 607 times negative 34 joules seconds times the speed of light, 299795458 meters per second. That's again in the data table. And then you're going to use the energy that you just found, 2.1619 times 10 to the minus 18 joules. And I have lambda is equal to 9.1884 times 10 to the minus 8 meters. All right, that is a very cumbersome unit, 10 to the negative 8 meters. So I would put it in a more convenient meters. So I want something that's going to be, you know, in the tens or singles or tens units. And so if I multiply that by 1 billion, I would get that as, so in 1 meter, or in 1 nanometer, there's 1 times 10 to the negative 9 meters. And so that will end up being 91.9 nanometers. That's a more easy unit. And so the wavelength going from 1 to 11, okay, that's absorbing, is going to then emit a color equal to the wavelength of 91.9 nanometers of light.